Hey, this is Mr. Soy. Today we're going to be looking at a concept called sequences. And we're going to look at two different ones. We're going to look at arithmetic sequences and we're going to look at geometric sequences. We're going to start off with arithmetic sequences because they tend to be linear in nature, linear relationship. And so I wanted to do a quick review of linear relationships from our first semester work. One of the things we discovered first semester is that if I can find a start value and a rate of change, then I can find an equation for a linear relationship, where essentially slope was my rate of change, and then the y-intercept was the start value. And we were able to then to put it in the equation y equals mx plus b, where I've got my slope and my y-intercept. When we started out, we were looking at block figures, and we typically were looking at x being the figure number, and then y being the number of blocks in that figure. And what we discovered was if we were given, say, figure 1 and figure 2, we could find the slope or rate of change between figure 1 and 2, and then we would have to go backwards to find the y-intercept, which was figure 0. And we did that by basically going in reverse with the slope in the opposite direction to figure out the number of tiles that would be in figure 0. Here's an example down here where we've got figure 1 has 3 tiles and figure 2 has 7 tiles. And we want to model this linear relationship using our equation. All right, well, the first question is, what's my rate of change, my slope? Well, if I look at figure 1 and it has 3 tiles and figure 2 has 7 tiles, well, how many tiles were added between figure 1 and figure 2? Well, 3 going to 7 is going to give me approximately 4 tiles. In other words, for every figure that I go, I'm going to add 4 more tiles from the previous figure. Excellent. The problem is I don't have figure 0. So I would actually have to go backwards, right, from figure 1 to figure 0. In this case, if I was going to do that, well, I'd end up with a negative number, because 3 minus 4 going backwards is going to give me a negative 1. And so our equation then would end up being, that would model this linear relationship, would be y equals 4x minus 1. Okay, so the reason we wanted to review linear relationships is because we have this new concept called an arithmetic sequence, which is also linear. And if we take a look at the one that I've defined here, t of n equals, and then I have this sequence kind of spread out. Well, we're actually going to get a formula for t of n, but right now you can see that it's giving me values. These are discrete values, and those discrete values then have a rate of change as we move from one to the next. Well, let's describe what t of n really means. T, it's kind of function notation, and t is essentially like term. And we call each of these individual things in a sequence a term. Term 1, term 2, term 3, you get the idea, and we go. The dot, dot, dot at the end means that this sequence goes on forever. Okay, so t means term, n is which number in my sequence is this term. In other words, n equals 1 here for the first term, n equals 2 here for the second term, n equals 3, n equals 4, 5, you get the idea. So when we plug in a number into t of, so let's say t of 4, I'm looking for the fourth term in that sequence. And I just start at the beginning and I go out 1, 2, 3, 4. And so t of 4 would be 8. And that's the idea of a sequence and this function notation for it. So terms, basically we have this concept of a rate of change. We know it as slope, but in arithmetic sequences we call it the common difference d. Well, looking at the example I have here, you'll note that as I go from 2 to 4, I'm increasing by 2, 4 to 6 increasing by 2, 6 to 8 increasing by 2, and we get the idea on and on and on. That means I must have a rate of change or common difference of 2, because as I look at the rate of change between each subsequent term, I'm basically adding 2 each time. And we've done something similar when we've been presented with tables of data, linear data, back in first semester, and we were trying to find that rate of change, that change going from one table entry to the next table entry. It's the same concept here. What is the common difference between subsequent terms? In this case, I'm just looking for that rate of change. In this case, 2. But instead of using m for slope, we call it common difference and use the letter d. And in this case, it's plus 2. Then we have this idea of a start value, just like we have in linear equations. And notice here that we have a slight variation from what we might consider the first versus 0 term. When I list out a sequence like 2, 4, 6, 8, 10, the very first one I see in the list, that really is t of 1. It's the first term. And so the 0 term, just like when we were looking at block figures, can be achieved or found simply by going backwards. So in this example, let's say, you can see that the first term, t of 1, well, that's equal to 2. And then the t of 0, I would have to go backwards. Well, going backwards, I'm going to subtract my common difference off of t of 1. And 2 minus 2 would give me a 0. So in this case, t of 0 for this sequence would be 0. Okay, so I think you can see what this relationship is. It is linear. We're looking at a linear relationship with a couple differences from what we've looked at first semester. One, the n, or counter, as I like to call it, which tells us which number the term is in the sequence, it's an integer. We're not going to plug in numbers that are fractions like t of 1/2 or something like that. We're always going to plug in integers starting from 0 moving up. And so we have n being an element of the integers. That's what this means up here, element of the integers. And it's positive. And so that's because we're actually counting numbers in a sequence. Okay. Between any two numbers in that sequence, there are no values. And that's what we've been calling a discrete function. And these are functions. And it's discrete because it's individual points as opposed to a continuous line like in a linear equation. But otherwise, there's a lot of similarity here between a linear equation that we've already learned and know and this new concept called an arithmetic sequence. Okay, well, let's take a look here at this function notation then. T of n is equal to t of 0 plus d times n, where n is our counter. And so notice that it's very similar to y equals mx plus b, where t of 0 is going to be the start value. We also know that as the y-intercept. D, our common difference, well, we also know that in linear equations as our slope. And then our counter n, right, basically is like variable x that we normally plug in, except here n is very restricted. N is only an element of the integers greater or equal to 0. And so we can create a formula, essentially, or a function based on the example from the previous page because we knew our t of 0 and we knew our common difference. And so if I write that out, it would look like the following. T of n is equal to t of 0, which was 2, plus our common difference, which we also found to be 2, times n. And in this notation, this function notation, I can now calculate what any term in that sequence, what their value is. So let's say I wanted to do something like t of 10. I want to find what the 10th term of this sequence is equal to. Well, I'm just going to replace, like we have in the past, the x with the number. I'm now going to replace the n with the number. And when I do that, I get 2 plus 2 times n, but n is 10. And so I get 2 plus 20, which is equal to 22. And so the 10th term in our sequence is 22, t of 10. And that's how the function notation works. Because n is restricted to be only integers, we're going to only get discrete values that we plug into the function output. And so I could generate a whole sequence as far out as I wanted to using this notation and using this function idea where I can just keep plugging in values. Well, discrete, as a reminder, they're basically individual points not connected those are discrete values, and you can put them in set notation, you can put them in sequence notation, and the idea is I've got these individual points, but the values in between one point and the next, there are no values that exist. Continuous, on the other hand, well, we already know that. That's all points along line. In other words, when we graph a line, every single real number that's a point on that line exists. And that's the difference between discrete and continuous. Arithmetic sequences, and all sequences, in fact, are always going to be discrete, as opposed to our equations where we know that they are continuous. Okay, let's take a look at some more examples. And all we're trying to do is we're trying to find our common difference, our t of 0, and then from that we're basically going to create this formula. And in this case, the formula is going to be t of 0 plus d times n. So just like in the previous page. So let's take a look at this sequence. We have 3, 8, 13, 18, 23, and then it goes on that same pattern infinitely. Well, what we're trying to find is we're trying to find the common difference. Well, the common difference is simply that. It's the difference between subsequent terms. So when I take a look at the difference between 3 and 8, I can see to go from 3 to 8, I have to add 5. And then I do the exact same thing, and I can see I add 5, add 5, add 5, and that would go on to infinity. We keep adding 5 to get to the next term in the sequence. That tells me my common difference is positive 5. Now, we have the first term right here. This is t of 1. I need t of 0. And so I use my common difference and I go backwards. If I'm adding 5 going forward, I'm going to subtract 5 going backwards. And so I end up with 3 minus 5, which would give me a t of 0 of negative 2. And so then t of n is going to be simply negative 2 plus my common difference, 5 times n. And now I could get any term I want in that sequence by simply plugging in the term number for n, and then solving. Let's look at the next one. Same situation. I'm looking for the common difference, so I'm looking for the change as I go from one term to the next. 5 to 7, that gives me a change of positive 7, 5 to 12. And then 12 to 19, positive 7. 19 to 26, positive 7. 26 to 33, positive 7. And so just like in the previous one, my common difference then is going to be positive 7. T of 0 then, well, again, I've got T of 1, the first term. I need T of 0. The way that I'm going to get it is I'm going to take my common difference and go backwards from 5 or from T of 1. 5 minus 7 would give me a T of 0 of negative 2. And so now I can write out my formula. I've got T of n equals negative 2 plus my common difference, which is 7, times my counter or term number, n. And again, I can plug in any value I want to get any term I want. For example, let's say I wanted to know what T of 11 is. Then I just simply plug in n equal 11 into this equation, and when I do that, I end up with the following: negative 2 plus 77, and so I find that the 11th term is the number 75. And that's an arithmetic sequence where we're given a sequence, we find the common difference, we find T of 0, we write down the relationship, equation, formula, and then we can use that to calculate any term, what the value of any term is in that particular sequence. All right, so we're going to finish off this lesson by looking at another type of sequence called a geometric sequence. And basically the idea behind it is that instead of adding a common difference each time, I'm actually going to multiply by a common number, and we call that number a ratio. And so we want to go back and look at lesson 511, where we're looking at Lenny and George and the rabbits, and they were going to raise rabbits. And if you recall, they talked about how they were going to start with 2 rabbits, and that those would produce 2 rabbits, and then those and the previous ones would produce 2 each month, going on and on and on. And so the number of rabbits you figured out per month, you modeled and created a table for it. And in fact, we can see here in this sequence right here, we have that data. So start at month 0 with 2 rabbits. Month 1, you've got 4. Month 3, you now have, 0, 1. At month 2, you now have 8. Then at month 3, you have 16. Then 32, then 64, and you keep going up. And I think after a year, it was 8,192 rabbits, right after 1 year. And what we found is that those rabbits were essentially doubling. They were doubling each month. And doubling means I multiply by 2. That's how we double things. We multiply by 2. And it's that multiplier, okay, that makes the difference, as opposed to a common difference where we're adding the same number from sequence term to sequence term. Now we're actually multiplying by this multiplier. It's also known as a common ratio. Let's take a look at this and see how that works. So if we were dealing with a sequence, then we would have T of n, where n in this case would be the number of months, or month number, and we could look and see what the values are for each of those as we go month to month. Now, we can see them in the sequence above, but what we're going to actually do is look at it more from a calculation standpoint. All right, so t of 0 is kind of our start value. In this case, we're looking at time, n is time, and at month 0, it's however many rabbits they start with. And so in this case, it would have to be 2, because that's how many rabbits they started with at the very beginning. That's month 0. After month 0, it doubles. And so we have our t of 0, the previous term in the sequence, and we're just going to multiply that times this multiplier, which doubles things, 2. Okay, well, t of 0, we already know what that is. That's 2. And then we're going to multiply that times 2. And so for t of 1, I end up with 4, which we can see up here is exactly correct. And I can continue this, and I end up with, well, it's always going to be t of 0 that I start with. Then I multiplied by 2, but then I had to double it again, because again, I'm moving on, and each time I move on, I double it. And you can see how we can continue this pattern, and that ends up being 8. And then I'll do one more. So now it's t of 0. Double it, that gave me t of 1. Double it again, t of 2. And now I have to double that again to get t of 3, giving me 2 times 2 times 2 times 2. And that's equal to 16. And we could keep going on like that. Well, look, let's see what kind of pattern we've got here. Notice that I purposely put in t of 0 each time. That's my start value. Start value, okay. We know that term. It's t of 0, right? Start value. Oftentimes it's also y-intercept, right? But now I've got this new thing right here, the multiplier. And the multiplier, well, we just keep multiplying by that, also known as a common ratio, each time that we want to increase the term number. We know how to write that when we're essentially multiplying by the same number over and over again. Let me show you what I mean. If I have t of n, then basically that would be equal to, again, the start value, t of 0. And it would be 2 times itself n times. Because look, if I look here at t of 3, how many times did I multiply the multiplier? 1, 2, 3. 1, 2, 3 times. So if I have n here, then I would multiply the 2 here n times. Okay, I know how to write that. We know that as an exponent. I can write the multiplier raised to the term number, in this case, n. And so really, all of these could be written in that same way. For example, t of 0 is equal to t of 0 times my multiplier 2 to the 0 power. But I already know what 2 to the 0 power is. It's 1. And so I'd end up with just t of 0, which we already knew is 2. Here, for t of 1, that would be t of 0. And that would be times my multiplier, 2, raised to the 1 power. Well, t of 0 is 2. 2 to the 1 is 2, and I get my 4. And I can keep going down the line. This would be t of 0 times my multiplier, 2, raised to the 2nd power. And I get 2 times 2 squared. Well, that's 2 times 4, 8. And we keep going. And so we actually can develop this exponential formula or equation for a geometric sequence using this multiplier raising it to the power of n. They're nonlinear. They're exponential equations. And that's what it looks like as a sequence. We're going to be working on these in a lot more detail, especially when we get to chapter 7 and we look at exponential functions. But in this unit, we're focusing on sequences, and so we've introduced this exponential growth with the rabbits. I've now introduced this geometric sequence concept where we're able to derive a function that gives us any term in a geometric sequence using a multiplier raised to the power of n, which is my term number. Thanks for listening today. Take care.